We're still looking at the line through 4, 7, negative 2, parallel to v equals negative 2i plus 4j minus 3k. A picture of the situation would start with a point representing 4, 7, negative 2, and a vector representing negative 2i plus 4j minus 3k. If we multiply this vector by 2, let's say, then this vector would be, the red vector, would be 2 times negative 2i plus 4j minus 3k. And the point that we end up with would be 4, 7, negative 2 minus 4, 8, and negative 6. Not sure that 3k is very legible, but hopefully you understand what I mean. If we draw a general point on the line, well, again, if we double this vector and displace from this point to the resulting point, that vector will be on the line. If we multiply this vector by any number, it's going to give us a point on the same line, so that the general form of a point on this line would be to start with this vector and proceed along the vector t times negative 2i plus 4j minus 3k. That would represent the displacement vector from here to here. So that our point x, y, z in general would be 4, 7, negative 2 plus t times our v vector, negative 2i plus 4j minus 3k. If we set these two equal and regard this as a displacement and regard these two points as vectors, we obtain the same equations we saw before, our parametric equations, and we have already seen these. So this gives us our parametric equations for the line. Now, as we mentioned before, we can alternatively, as an alternative, solve these equations for t. This equation gives us t equals x minus 4 over negative 2, so we'll write that as negative x minus 4 over 2. This equation gives us t equals y minus 7 over 4, and this equation gives us t equals negative z plus 2 over 3. Now, each of these expressions is equal to the same expression t, so we can express the parametric equations in the form of what we call the symmetric equations for the same line. And the symmetric equations read negative quantity x minus 4 over 2 equals y minus 7 over 4 equals negative, better put some parentheses there to make sure it's clear, negative the quantity z plus 2 over 3. Now, each of these equations, the symmetric equations and the parametric equations, is equivalent to this condition pictured here, and also equivalent to the conditions we stated earlier on the preceding page, that this vector be parallel to this vector with constant t intermediating our proportionality. It should be clear that the vector v, 2i plus 4j minus 3k, appears in the denominator of the symmetric equations. It appears as the coefficients of t in the parametric equations. And our point 4, 7, negative 2 is represented in the parametric equations. Here's 4, 7, negative 2. In the symmetric equations, here's our 4, here's our 7, and here's our negative 2. Now it's minus the 4, minus the 7, minus the negative 2, which makes it, of course, plus 2. So that these equations and these conditions are all completely equivalent to one another.